The broadcast is now starting. All attendees are in listen-only mode.
Hi, everyone. Thanks for joining us. Welcome to the weeks 3-4 S2S webinar series. I hope you can all hear me and see my screen and everything fine. As many of you are aware, this series is co-sponsored by the OIR Weather Program Office, S2S program, and the Weather Service OSTI modeling program. I'm Mark Olson, part of the S2S program in the Weather Program Office. So today, as usual, we have two really good talks. But before we begin, once again, I want to remind everyone of the webinar series website, and I'll post the address in the chat box as soon as I'm done talking here. But you should be able to see that on your screen there. But on this site, you can see information on the upcoming talks, and you can add yourself to the mailing list if you haven't already, and access the recordings of past talks. And also, as I say every month, I think, perhaps most importantly, is a form available if you're interested in presenting in a future webinar, just to kind of spread the knowledge of your work. So we have some spots. We're going to end up taking December and January off because of the holidays and AMS and AGU and all the busy time during these 2 months. And then we'll resume back in February. And then I think we've got a few spots open shortly after that. So appreciate it if you care to let us know that you'd like to present, and we'll work with you to find a time. So finally, if you have any questions for the speakers during the presentation, post them in the discussion document. It's actually in the chat. I'll probably periodically repost it in the chat just so you can see it if it floats up off the chat window. So anyway, today we have two presentations. Judah Cohen's going to speak about machine learning and the S2S forecasting. After that, Dan Collins is going to speak about work that they're doing on calibration of subseasonal model forecasts. So let's go ahead and get started, and I'll turn it over to Judah. Judah, let me make you a presenter here. There you go.
Okay. All right, great. Thanks so much, Mark. And also, thank you for the opportunity to present our research. This has been very much a collaborative effort across universities, industry, and all the way stretching from Canada to Brazil. I'm presenting today, but I do want to give a special shout out to Sonia Tots, who's done the lion's share of this work. And she is a postdoc in the Civil Environmental Engineering Department at MIT. Okay, so I guess for this crowd, the slide maybe is not needed, but subseasonal forecasting is important. Subseasonal forecasting of both precipitation and temperature. So that's typically subseasonal is thought of everything less than a season, but I think everybody thinks of it as week 3 through week 6. So I guess your webinar series focuses on week 3 and 4. But we can see where it can be important for allocating water resources, and managing wildfires, preparing for weather extremes, including droughts, heavy rainfall, flooding, for crops, irrigation, and also for energy. And here's a couple citations, highlighting the importance of this time frame in forecasting and weather events, on our society. So certainly, improvements in this time frame would be very beneficial. So there's a slide from IRI, a very simple slide, but I think very nicely conveys the skill, the accuracy of different forecasts at different time ranges. So, weather forecasts are typically, from the next few hours to out to maybe 2 weeks. We have excellent forecast skill in the shorter ranges, but that quickly drops off, and that's an initial value problem. And then you have less skill, but there have been advances there slowly in the like in the seasonal time range, what we might call the climate forecast, and most of the skill has come from our knowledge of the El Nino Southern Oscillation, and that's really a boundary value problem. And in between those two time frames is the subseasonal, again, like weeks 3 through week 6 typically, maybe a little longer, and that has the least skill, or the poorest accuracy in the forecasting, because it's too long to be an initial value problem and too short to be a boundary value problem. And kind of like the holy grail of making improvement is in this subseasonal time frame. So we've been trying to capitalize or exploit machine learning to improve the subseasonal forecast. So like the cartoon on the right, kind of shows it's for a lot of people. Oh, I don't know if there's a automatic advance button there. Sorry about that. It's a little bit of a black box. You kind of have linear algebra to, these equations set up a linear algebra to manipulate a lot of data. You get an answer, maybe you're not happy with it. You just keep stirring until you get the answer you want. But we do think that machine learning and data science have had a long history in atmospheric sciences. Processing much larger data sets with new machine learning techniques can improve models of forecasting. So that's what we're trying to do. We still need to understand the underlying physics and chemistry to select the data method. The machine student needs an intelligent teacher, and certainly, our group has this mixture of data scientists and meteorologists. I think that combination is really necessary to get beneficial results. While machine learning can be computationally expensive and hard to interpret, it can also find new features and generate new research questions. And I myself, when wearing a different hat, is more interested in stratospheric troposphere coupling, and I think that's certainly been true in that area. So dynamical models have many, they certainly have come a long way in the past few decades, but they still have shortcomings that can be revealed and improved with the help of data analysis. So one area, so this talk will provide 2 different machine learning techniques or approaches to help improve the forecasts from dynamical models. The first one we call adaptive bias correction. So you have a dynamical model, and there are 3 corrections. So the first one we label dynamical plus plus. That averages the dynamical forecast over a range of dates and lead times. And based on how the models have performed recently, the forecasts are corrected. And I think that is probably what people are most familiar with just kind of more traditional bias corrections. But it does learn adaptively. It's not frozen. And as more forecasts become available, the information is updated, and this debiasing is corrected and updated as well. Also, persistence, looking back historically a short time ago and using past lag temperature precipitation to adjust the dynamical forecast. And also the third one is not really involved in dynamical models, but just some kind of climatology. We call it climatology plus plus. And again, it continuously updates the climatology, based on historical mean and geographic median, wind and over target day of the year. And again, this is updated adaptively. And the 3 of them are then combined together to give you a corrected dynamical, model forecast. So here's an example of how this adaptive bias correction, which is again a combination of physics, what's the basis of the dynamical models plus this hybrid learning model. So here, for precipitation, weeks 3 and 4, weeks 5 and 6. Here's the skill, the accuracy of the forecasts for both precipitation on the left and temperature on the right. This is so the top row is the raw CFS V2, and you can see modest skill. And the top number shows you the average over the entire contiguous 48 states. The middle row is for the more traditional debiased CFS-V2, like for instance what's used in the sub-X models. So for the most part, there's some improvement, but not necessarily a lot. And then the bottom row is our adaptive bias correction to the CFS-V2. So you can see there's certainly more coverage. So when you look at precipitation of positive skill, and for the entire U.S., those averages are higher for both. And this is the same for both precipitation and for temperature for both time periods, weeks 3 and 4 and 5, 6. And at least for the CFS version 2, it can double or triple the forecasting skill of this operational dynamical model. And here's looking at comparing the different the adaptive bias correction model with other baselines. So the debiased CFS version 2, which is what's basically used operationally, shown in the top row. Then just maybe using persistence. Here's some different machine learning models that we've tried to use, and a whole list of them. And then on the bottom, we've broken down the 3 components of the ABC model, and then the very bottom line is using all 3 components of this adaptive bias correction. And certainly the full adaptive bias correction provides the highest skill of all the different forecasts that we show here in the table. So it the CFS version 2 corrected with the ABC outperforms the operational US model in its raw or traditional debiasing and 7 state-of-the-art machine learning, deep learning methods that we've tried, and also from the literature. So it's not just us. But we're also using a method called cohort Shapley to, so not all the time does the ABC method lead to a better forecast. Sometimes it's better to use actually the more traditional debiasing that's currently in use. So with this cohort Shapley, we can kind of inform let's say the forecaster when to use the ABC, in real time, and when to forego it and just go with more traditional debiasing methods. So we use different variables. So like this first one on the left is geopotential heights at 500 millibars, and you can see MJO, sea ice, sea surface temperatures. I think I said maybe I mentioned MJO. The ENSO here all the way on the right. MEI version of ENSO. Multivariate ENSO index. But anyway, so and 500 millibar heights is the most important, gives the most weight to the forecast. But we'll show one example how that works. So we break down the 500 millibar height anomaly patterns into deciles. So you can see starting from 1 on the top left all the way to 10 on the bottom right. So the top left has low heights over the Arctic and positive height anomalies across the mid-latitudes, and should be familiar to like a positive Arctic oscillation. And 83% of the time when this pattern is observed, the ABC will outperform the more regular debiasing methods that are currently in use. However, this decile 9 looks like the negative Arctic oscillation, kind of the opposite of decile 1. So positive heights over the Arctic and lower heights over the mid-latitudes. The ABC actually only outperforms the regular debiasing over only 12% of the time. So based on this information, if you're leading up to the forecast, this is the observed pattern, a positive AO is observed, you would you would use the ABC. If you saw a negative AO, you would just go with the regular debiasing. So ABC is more likely to outperform regular debiasing when you have a positive articulation, and least likely to outperform regular debiasing when you have, the opposite or negative Arctic oscillation. So here's shows you, how you can use this information in real time. So it's just a random example, but here you can see kind of this positive Arctic oscillation, low heights over the Arctic, positive heights in mid-latitudes. Here's the observed precipitation anomalies. Here's the debiased ECMWR forecast, so a total skill score of 26%. But the ABC gives you a much higher skill, almost double, of 46%. So you would see the positive AO, let's go with the ABC over the more traditional debiasing, and you're more likely to get an improved forecast. And this is how you, kind of use it, applied. So high impact variables mean when within the ABC is more likely to provide you an improved forecast over the regular. So obviously 0 more, that means that occurs 100% of the time. And it shows you the skill for the ABC versus the bias. And it seems like the sweet spot is kind of in the 2 or 3 more. So where the ABC will give you, if you have 2 to 3 high impact variables observed in the, prior to the forecast, you're more likely to have an improved forecast. But after a while, and there are many cases of that, but after a while, even you have 7, that would be, you think that's great, but it's only found 2% of the time. So here on the chart on the right, we show that. So the green is the ABC forecast for the number of high impact features. The blue is the the blue dash is just using ABC. The green solid is, the red kind of dash is just the regular debias. So typically the ABC outperforms, but the green is the combined, and that's where kind of you get the highest skill, and when you have 2 or 3 high impact features. Even though as you get more and more features of the ABC, the skill goes up, but it's found fewer and fewer times. So hopefully I explained that clearly. But you apply ABC opportunistically when multiple exploratory variables are high impact state, and use baseline debias, dynamical model otherwise. So it's basically looking for windows of opportunity to deploy ABC or regular, or just kind of default to the traditional debiasing. So we're going to move on. So besides looking at this ABC, which is a bias correction, we try to come up with a different ensembling method. And again, since the Climate Prediction Center uses probabilistic forecasts and a probabilistic forecast framework. So, like for example, we have 3. Usually, the Climate Prediction Center issues forecasts in the 3 categories: below normal, near normal, and above normal temperatures. And so we score, just like CBC, we're looking at the skill score based on the rank probability skill score. And this is just looking at the rank probability score of the forecast relative to some other benchmark, most commonly climatology. So if the rank probability score of the forecast is perfect, it would be 0, and you would have a rank probability skill score of 1. And then, if this was, can go as high as 1, a really poor forecast would be as high as 1. And you can see if the climatology does well, this can go to negative infinity. But a good forecast would be 1, a perfect forecast would be 1, and then it goes down from there. But hopefully, if you're above 0, you're doing better than a climatology forecast. So here we come. Again, I guess just showing different models. Maybe I jumped a little bit ahead, but here's looking at the rank probability skill score compared for different, seasonal forecast models. Show here the raw in green. The blue is the sub-X models with their traditional debiasing, and then the ABC. So like for a really good model, such as the ECMWF, The ABC, shows somewhat improvement, but not a lot over this, the traditional debiasing. For some poorer models, like on here on the right, like even the CFS, it's a very large improvement. So on the left is temperature, and I think generally precipitation, the improvements are more impressive than for precipitation. But I want, this will be more for the end of the talk. You can see once you apply ABC, even the poorest models come into line with the best models. So there's not much difference in the skill of all the models once you've applied ABC. Whereas there's a much bigger difference if you use the raw, or even if you use the traditional debiasing, you can have a very large range of accuracy or skill among the models. So for example, here the blue means, poor skill, negative skill, and these oranges and reds are positive skill. So here would be, for example, for its temperature forecast, you see much of using the raw data, it's, most of the country is in blue or negative skill. Once you debias, you get a modest positive, and then applying ABC is better, but only slightly better. Again, this is for a good model like the ECMWF, but it'd be more dramatic for poor, and as I showed earlier for the CFS. So we also use online learning. I don't want to get too much into how it's defined in the equations, but in general, you're just trying to minimize the regret. So you're looking for what is your real-time forecast loss minus the loss if you use just the single best model. So the smaller that number gets, you want to get that number as small as possible. So if you have different models, and you're trying to weight more heavily the best performing model, right? So we want an ensemble that has, the smallest regret. And this, I know this is a busy slide here, and I just really there are different versions. Right now we're using this DORM plus, delayed optimistic online mirrored descent, and I'm really not going to get into it. So there's a conservative choice, which is pretty much what's used now. You just weight all the models equally. The most aggressive is like the human would just say, oh, this model, let's say the ECMW did the best in the last forecast, we'll weigh that 100%, and weight all the other 0. But you can do very well, but you can also do very poorly, and it's highly variable, your skill score. We kind of want to get in between, where we're using more objective methods to weight the model. So it's more aggressive than just equal weight, but not as aggressive maybe as a human forecaster might be. So again, here's the sub X, kind of equal weight debias. So a lot of the country, so almost equal to climatology, but a lot of the country is blue or negative skill. And you get, if you use this online learning for using the sub X as traditional debiasing, now much of the country shows positive skill. Still it's a modest overall, but most grid boxes are positive, and you can see the difference between your equal weighting and the online learning. It gives you positive skill for much of the improved skill for much of the country. Now the problem becomes is that once you've applied ABC, and now all the models have very similar skill or accuracy, then online learning gives you very little improvement, because there's not a large discrepancy between the skill of the different models, and you can see it's very modest, the improvement. And looking at like a time series, so you can see the online learning is blue, and just using an equal weight after you've applied debiasing, ABC debiasing, it's only a modest improvement overall. I mean, it is an improvement, but you've gained most of that improvement from first applying the ABC. So in summary, ABC can double, triple forecasting accuracy of operational models, especially those that are poor, and can put them on equal footing, kind of giving them accuracy as the best performing models. We've also been trying to apply this cohort Shapely, where it tells you when you should go with when the ABC is likely to give you an improved forecast, or where maybe more traditional debiasing will give you a better forecast. As we're learning, using adaptive ensembling, and the example I showed here is online learning, is only successful when the skills and model predictions differ sufficiently from each other, and when they're of equal skill, then online learning is, gives you less benefit. So I thank you very much, and I also want to thank support from the Weather Program Office for funding our research.
Thank you, Judah. Are there any questions from the audience? I don't see anything in the document here. If anybody has any question that they want to ask, they can probably unmute themselves and ask, or just type it in the chat here really quick. While we're waiting, I had one question for you. So the ABC model and method, is that like now fully tuned? Is there still some like little knobs or anything that you can twist on there to try to even improve beyond some of those large gains that you actually see already? Or is that pretty much fully tuned to where you think that's probably maxes out the improvements that you can see in the skill?
Yeah, so I mean that's something we're kind of struggling with ourselves, where to say enough is enough. Again, so this is a research operation project, and we have to, we want to hand off to CPC the software. So I think we're working more now. We feel pretty good about the ABC, and we have a paper in review on it. So I think we're working more on the online learning sphere, but I think it could always be attuned. And again, of course, it's always taking in new information and adapting as more and more forecasts are made. But the original tuning takes a very long time, and I think we're pretty much settled on that. But once it's implemented, it does update with the new forecasts.
Great, thank you.
Yeah.
Any other questions? I do see, okay.
Yeah, I see that. That's an interesting question. So I mean, there was that table, right, that breaks down the different skill of the different components. So the worst is just using climatology, and using using past forecasts and devising, and also persistence. This adaptive persistence gives you the most improvement. So it's so it seems to be a combination of the dynamical models itself and also from recent recent observations. This longer term climatology doesn't give you as much improvement. So I don't know if that, again, Sonia knows the nuts and bolts of this work better than I do. I know she's, I'm sure, I assume she's on the call. I haven't looked, but I don't know if she's muted or if she can, type in the chat. But she knows better than I do.
Okay. Time for like one more question, if somebody has it. Let's see. There is a question being typed into the document here. Matt Rosenkrantz, I guess, asks, what is CFS V2++?
Yeah, so I think it's, and again, Sonia would know better. I think it's kind of similar to to more traditional debiasing. Comparing the forecast from the model with the observations, and then so if there's a cold bias, removing that cold bias. But I think the difference is that the bias isn't kind of set in stone and never change. It's updated and it's updated adaptively. So as more information comes in, that dynamical model is that debiasing based on the forecast is updated. So again, hopefully I explained that correctly. So CFS V2 means it's every model so we call it plus plus. So ECWF plus plus CFS plus plus GEFS plus plus. I mean, just I think it's very similar to traditional debiasing, but what's new here is that it's updated as new information, as new forecasts come in.
Great, thank you very much. We should move on now to Dan, and okay, I'm going to make you presenter here. And I'll let you present your screen and start when you want.
All right, thank you. Thank you, Mark. You can see, I assume. Looks good.
Yep.
Great, thank you. Yes, so thanks again for the opportunity to present at the webinar. This is some work that we built through some prior funded proposals, actually 2 on the development end. And this is a proposal that is now in a stage of moving components into operations at the subseasonal time scale. So what I'm going to present is a combination of information from the prior work. This is all related to Bayesian joint probability calibration of subseasonal model forecasts. And you can see my co-authors there. Special thanks to John Infanti helping to put together this presentation, and Sarah Strazo was our contract scientist who developed much of the software at CPC, and that's our Australian collaborators, QJ Wang and Andrew Sheppin, who developed the methodology of BJP, or Bayesian joint probability forecasts. Okay, there we go. Just for many of you, I'm sure you're familiar with CPC forecast, but just to orient ourselves and make sure that understand what this tool BJP is going to be used for ultimately when it's in operations at CPC. We have the week 3-4 outlooks. That shows the outlook page on the left. This is a 2-category forecast, but it's intended to transition into our more traditional CPC 3-category forecast with above normal, near normal, and below normal in the future. But this was an experiment in something a bit different, 2-category forecasts as it was begun at CPC for weeks 3-4. So you can see that temperature probabilities are calculated with respect to the above and below the mean. Precipitation probabilities are calculated as above and below the median forecast in this 2-category system. There's multiple tools that go into our forecast to give you a window into how this is generated. The forecaster creating the official outlook will use various dynamical model tools as well as statistical models, and that includes the certain indices of the climate state, such as MJO, as Judah noted, very important for subseasonal week 3-4 timescale. There's a discussion included with the forecast, and that provides information on what the tools were that were considered, what was weighted, what the climate drivers were that should have played a role in the forecast, as well as various areas on the map that there was confidence or lesser confidence in the forecast. So this system is about calibration of the models. So that's statistical post-processing of the dynamical climate model output and trying to improve the skill and the reliability of probabilities. We do the calibration because the dynamical model forecasts, they do have skill in forecasting the climate features and the large-scale circulation, but they generally are biased due to systematic errors. And they also, through ensemble models, we can generate probabilities, but they tend to be unreliable in determining the actual likelihood of above normal, below normal, et cetera. So the central problem of dynamic models is the parameterization of the physical processes. And we can try to improve model physics parameterizations, or we can increase model resolution, or we can change the dynamical core of the model. But all of these are expensive computationally and require changes to the model itself and rerunning of hindcasts, et cetera. So Alternatively, at much less computational expense, we can do post-processing or statistical calibration of the probabilistic forecasts. And that's what the Bayesian joint probability calibration system is, or BJP I will use for short. This was developed, as noted, in collaboration with Australian scientists from CSIRO. There were 2 prior projects related to the development of this system. And we generate both subseasonal and seasonal prediction tools using various dynamical models that we have available at subseasonal and seasonal timescales to do these forecasts. And you can see maps there across the bottom of the page that shows various subseasonal and seasonal forecasts that we have. We have subseasonal temperature currently for the subseasonal, we have only temperature for the subseasonal timescale currently in terms of a tool, an actual output tool. We've begun work on precipitation on the subseasonal timescale, but right now we only have a seasonal precipitation tool. Calibration, that's relating the dynamical model output of to the observed climate variables and correcting the model bias, also correcting the spread, as I said, the probabilities that we get from a dynamical model, ensemble model system, or a multi-model system as well, would tend to be unreliable in terms of actually determining the frequency of above normal or below normal. The calibration process returns probabilistic forecasts to climatological probabilities. So for 2-category forecast, that's a 50-50 chance. So determining when the skill of the information is absent is actually quite important, and returning a forecast that's closer to climatology or weaker probabilities. The BJP calibration in particular, this relates the GCM output to the observations just as any calibration system, but it uses this process of generating a continuous bivariate normal distribution, as well as using a Monte Carlo Markov chain resampling technique and generating 1,000 statistical ensemble members. So what that actually means is that there are 1,000 different estimates of the relationship between the observations and the hindcasts made, and through sampling through this Monte Carlo Markov chain resampling technique. And that generates this statistical ensemble. That's very large, you might say, but we've done some work around that. Once we generate the 1,000 members, we actually subset it to 200 members to store. But that process, I won't go into in further detail. So this repeats somewhat of what I said on the previous slide, but I just wanted to show it with this image on the right to give you a sense of what the bivariate normal distribution means. So we have a distribution for observed temperature, we have a distribution for the climate model, and temperature or precipitation in the case of the seasonal, we've done the same thing. And then for precipitation, you have, of course, a transformation to make a normal distribution before you can apply the technique fully. But there's transformation software that is part of the BJP system. And then you get these estimates of the relationship of those distributions between model and observations. And you do that, as I noted, 1,000 times over. So looking at some information on the skill, we began this project, or that is looking at BJP for the seasonal timescale. That's essentially was the separation between the 2 projects, other projects that I noted. So on the seasonal timescale, we use the North American multi-model ensemble, which also includes, of course, the NCEP CFS V2 system. So on the right, what you see is the Breyer skill score difference for the full NMME ensemble. As can be the case, the NMME ensemble, the full ensemble, is more skillful than any individual model on average. And it tends to be more reliable probabilistically as well as you combine different models. However, if you apply the calibration system, you can see that the difference on the right shows you that in those areas of red shading, that you do get definite increases in skill in various areas and various seasons between the calibrated and uncalibrated system. And we can do the same thing for precipitation. As I noted, this slide shows the same as the last slide, but for precipitation, again, Breyer skills score, a probabilistic measure of skill, which is essentially the difference between mean squared difference between the probability forecast for the correct category or for the above or below normal, and the difference from the ones and zeros that make up when you actually get above normal or not. But actually, this is for the lower tercile, but there's no real difference in calculating. Oh, these are tercile forecasts, sorry. These are tercile forecasts because this is the season. So on the seasonal timescale, we do it in terciles. So again, as I said, the subseasonal will be transitioning to a tercile forecast as well. And we've already applied it in the tercile system for the seasonal forecasts. So this is again showing the seasonal calibration with the BJP, and in this case, we're looking at reliability. And the size of the circles that you see there, that's showing you the relative number of forecasts that you have in each category. That is not in each category really, in each bin for probability. So you have probability bins there from 0% to 100%. I believe there are 10 bins. And you can see that actually the larger circles are around the tercile forecast, so they actually clustered around 33%. You get that even in the raw forecasts, but you get a greater number of forecasts with greater confidence in the raw forecasts. Though those forecasts, you can see they're generally overconfident. The line for the black raw probabilistic forecast from the multi-model ensemble tilts below the dashed line, so that indicates that it forecasts higher probability when in fact the frequency of events is less than what is forecast. However, the CBAM in this case, which I'm not going to go into in detail, which combines the BJP methodology with a statistical component as well in a hybrid forecast. But in any case, both the statistical component and the calibration component use the BJP, and you get this more reliable result where in each season the reliability lines up more with the diagonal. So when you forecast a probability, that represents the frequency in which the event occurs. So in terms of subseasonal timescale, as I said, we applied this to seasonal on both temperature and precipitation. Then in subseasonal timescale, we've begun work on precipitation and we applied it in temperature. We're calibrating the sub-X or subseasonal experiment models with the BJP. In fact, we do a 3-model subset or mini MME. The reason for that is because of matching easily the initialization of the models on Wednesdays. We make the forecast weekly for week 3-4 at CPC on Fridays. And so it's easy to pull in the Wednesday forecast. We can pull in operations the Thursday forecast, but because this is non-operational and making sure that the forecast could be assembled prior to the Friday release, we use the Wednesday starts. We had 3 models from the sub-X that had Wednesday starts. Other models had other starts. So we did the calibration of each of the individual 3 models. We aligned the lead time with the actual operational outlook that's released on Friday. So that moves you from 15 to 28 days to 17 to 30 days. We developed the calibration model for every week of the year and every dynamical model. So there's 3 times 52 different BJP calibrations that are done here. It does pull in information from bounding weeks, so you're not just using that week in the hindcast, in fact, but you're using some weeks in the future and some weeks in the past. But we're shifting forward with every week and recalibrating so that the model gradually, the BJP system calibration changes over time. And then you combine 3 models, and we've done an equal weighting combination. We've also done a weighting continuous rank probability skill score, determining what the weights should be for the three different models. Currently, for the subseasonal, it's only been applied to 2 category, is what I lastly noted there. So here's some examples of the products that we have from the subseasonal calibration of these 3 sub-X models.
Yeah. The weather is looking better.
Judah, I think that, all right. All right, thanks. So in any case, this is some examples of some of the products. We have actually quite a number of forecast maps. And this is used by the CPC International Desk as well as for the US outlooks. So the International Desk is interested in various regions around the globe, including Africa. So that's what you see on the right. Is you see the subseasonal calibration systems and on the right for Africa. And then on the left, you see the North American region, including, of course, the US and the subseasonal calibration there. For precipitation, actually, we're using a different calibration system, which I'll allude to at the moment. So we're producing a product from this extended logistic regression, or ELR. And those are the maps for precipitation shown on the pages here. So looking at subseasonal skill from the BJP calibrated system versus the raw model output. When I say raw model output, this is bias corrected relative to the hindcast climatology. These are for the GEFS v12, or the latest version of the GEFS. So these are Breyer skill score, once again, and on the left, those 12 panels are for the months, the Breyer skill score. Anything positive is greater skill than climatology. So in the Breyer, the numbers would be relatively low. This relates to the probabilities that you can put above the climatological 50-50%. And so you generally get relatively low looking numbers that are 5, 10, 15% above climatology. So that's why you see those relatively weak colors on the map. But you can see that it's either just above 0 or positive skill after calibration. Whereas if you look at the raw forecasts, you have quite a few areas of negative skill where the probabilistic information coming out of the raw model is not as skillful as climatology. So this is this is for the GEFS v12. And the second slide here is for the multi-model ensemble, the 3-model multi-model ensemble, which uses the Esrael experimental FIM model, the GEFS v12, and the CFS v2. So for that, the raw combination of the 3 models is more skillful than the individual model. I'll flip back momentarily. This is the GEFS v12, and that's the multi-model ensemble. So you can see we're starting with a point where you have greater skill because the multi-model ensemble adds skill relative to any individual model. But then the calibration, it would appear, adds skill on top of the multi-model ensemble combination. And if you look at the difference between the calibrated multi-model ensemble and the straight multi-model ensemble coming out of the models with just bias correction, the scale has changed here, so it's not as much gain perhaps as the colors might suggest to you initially looking at the previous map, but they are quite a bit, especially in those areas where the skill was negative. You certainly can bring the information back closer to climatology, and so you get definitely large gains in the areas where the skill was low or negative, and you get some gains virtually across a widespread area of the map. You get some gain in the Breyer skill score by calibration, which is what we would hope, that we'd be optimizing the probabilistic forecast information. Looking at reliability in the subseasonal timescale, this is the 2 category, looking at in the black, the 3-model multi-model ensemble directly from the 3 models and combined with equal weighting, and then the calibrated version is in the orange. You can see the individual calibrated models are the other three colors, the blue for GEPS, the green for FIM, and the purplish color for the CFS V2. Even the individual models, when they're calibrated, is an improvement in reliability relative to the raw multi-model ensemble. So even the multi-model ensemble relative to the individual calibrated forecasts, if you calibrate a single model, you do have gains in the reliability of probabilities, such that the probabilities more closely match the actual frequency of the occurrence of above and below normal. However, the multi-model ensemble tends to be the most reliable. Part of that is a gain in the number of ensemble members, but it's also a general increased skill in the multi-model ensemble, and then the combination of the calibrated multi-model ensemble. And so you have nearly near to the diagonal line in most categories. That is, I mean, in most probability bins. So you're very close to near perfect reliability. So the frequency is forecast pretty well after calibration. I went the wrong direction. Yes. Okay, there we go. So this is looking at the extreme bins or categories. So the 15th and the 85th percentile, below normal being the 15th percentile, and above the 85th percentile being extreme above normal forecast. We're not actually using this in an operational sense. This is something that CPC is interested in generating more information in the extremes. We do have similar forecasts on the week 2 and week 3 timescales for shorter periods. But just looking at the week 3-4 timescale and the extreme forecasts here as a kind of analysis and test of the potential to make these forecasts. You can see that for extreme forecasts, the calibration is actually very much essential. The forecasts are much too confident. The black line there, you can see it falls way below the diagonal line. And so whether you're below normal or forecasting above normal, extreme above normal, these forecasts are not very well calibrated coming out of the model. And there's much improvement through the calibration, even to the individual models, but especially so, again, the most reliable forecast is from the calibrated multi-model ensemble. And then we also at CPC, we often use this Heike skill score, which just to refresh anyone who's not familiar, this is really a modification to a hit rate. So it's when the category that is forecast to be most probable occurs simultaneously with the observation in that category, and then you get a hit. And the modification to the hit rate here is you're trying to compare this to a random forecast. This would be for 2-category forecasts, but for seasonal forecasts, we would be looking at a random choice of the 3 categories. So in a comparison to a random forecast, what % of the time are you forecasting the correct category more often than the random climatological forecast, in other words. And you can see here for this extreme above normal, I said reliability when I meant to really say there is extreme above normal Heike skill scores, but again, the 85th percentile. That the calibrated multi-model ensemble in comparison to the uncalibrated ensemble, that's black, or the individual models that's shown in the other colors, that is for this particular categorical forecast above the 85th percentile, it's always the most skillful in terms of correctly forecasting the extreme above normal category. These skill scores are not as high as for two category or 3-category forecasts. Extremes are more difficult to hit, but they do show positive skill, and they show that the calibration, once again, for the multi-model ensemble is essential, and the calibration of individual models is, again, more skillful than the multi-model ensemble without any calibration. So here's another comparison of skill, and I'll wind up in a minute here. This is comparing to the extended logistic regression. On the lower left there, those are histograms or bar charts showing the frequency in which the Heike skill score fell into different bins. So you see a distribution of various Heike skill scores that we get across the hindcast. The ELR is in blue, the BJP is in green. You can see a shift in the distribution. So you have a good forecast, you have bad forecasts. But in the mean, we jump from just below Heike skill score of 9 to above a Heike skill score of 25 on average after the in using the BJP calibration in comparison to the extended logistic regression. So I will note that so that's a different calibration system, and as I said, we're using it right now for precipitation on the subseasonal timescale. So it does seem that the BJP is an improvement over the extended logistic regression, and we would hope that we see that when we do the calibration of the precipitation. It is noteworthy that the observations that were used in the training of the calibration system by RI was also different than what we use for the BJP calibration and what we verify against. So that may play a role in the difference in these skill scores. They're both an improvement, though, over climatology. They're both a positive skill score relative to random chance forecast or against the raw forecast as well. They're both an improvement. So this is looking at seasonal once again. This is looking at grid points in which the Breyer skill score exceeds a minimum threshold of 0.1. This is a system of looking at the skill of the forecast and how widespread the skill is across the map. And so you can see that here we're comparing to a different calibration system that we use on seasonal timescale, the probability anomaly correlation, and we're also comparing to the raw forecast there in the gray. So in any case, relative to the probability anomaly correlation, we do have gains in skill in some of the models. It's a bit mixed for the 2-meter temperature, but in precipitation, it's pretty consistent that the calibration is an improvement in terms of the grid points that you have Breyer skill score over 0.1. And this is especially so for the NMME there. The box in red shows the NMME, the PAC calibrated or probably anomaly correlation calibrated forecast in light blue, the BJP calibrated in dark blue. And you can see that we've doubled nearly the number of grid points in which we meet this minimum threshold of Breyer skill score for the precipitation on the seasonal timescale. So that comes close to an end here. I'll just quickly go through this. I see we're running out of time, but we have this system in experimental forecasts applied to both experimental models and operation models. And our goal here, as I noted, is to move to operational forecasts on the subseasonal timescale for both temperature and precipitation. That means operational data streams and running it on the operational compute farm at CPC. It also means we'll be applying this to the subseasonal precipitation as we've done for seasonal precipitation. So the models that we'll be using are CFS-V2, ECMWF, GEFS-V12, and eventually the UFS as that comes online in the future. So I'll conclude here. Thank you.
Great, thank you very much. A couple questions have appeared in the document, and Jana is filling in some of the answers on that as we speak. And so we're running out of time here. Does anybody have a quick question at all? I will once again point out the document here for the questions and answers. If you do have a question that you come up with pretty quickly and you want to type it in there, the speakers are in the document, and they can answer in the document as well. So as we are out of time, I will say thank you to both Dan and Judah for some great presentations, and hopefully we will see you all back in February. And once again, go to the website. You can check out copies of the recordings and also sign up to give a presentation yourself. And hopefully we will see you all after the new year. So everyone have a great end of the year and enjoy AGU and AMS and all of that fun stuff too. So thank you.